Okay, so we are all set now, right?
So Çağdaş, sorry for interrupting. You can just proceed with you were introducing, I think.
Yeah, I think we sent everyone the short bio, but so everyone must have seen. But if Pedro wants to say anything to the people.
Yeah, no, I mean, I'm just with Carlos III here in Madrid, and I work on a few topics. One of them is fault-tolerant computing, and I have known Obud for quite some time. And the topic today is how to do fault-tolerant in machine learning. Very, very simple examples, but just introducing more conceptually the idea that these algorithms have some resilience in themselves that can be exploited for fault tolerance. So I think I can go ahead and then maybe if there are questions at the end, we can have a short discussion. Okay, so machine learning is now being, let me get this, is being used increasingly in many systems, and some of them are safety critical systems or systems in which errors are not acceptable. So there is a need to design reliable machine learning systems, and this is not a straightforward to do at a reasonable cost. So first, I will give a very brief introduction to machine learning based classification, which is the algorithms for which we're going to do fault tolerance, and then just look at very simple examples of some classifiers and how we can use the features of the classifier algorithms themselves to provide fault tolerance, or to at least reduce the cost of detecting and correcting faults. So in one of the tasks in machine learning is classification, which is one of the simplest tasks in machine learning or artificial intelligence, which is basically I'm given an element and I have to say if it belongs to place A or B. For example, I'm given a piece of code and I have to tell whether it's a normal program or it's malware. This can be patient, whether it has an illness or it doesn't have. You have many examples of this. Right? This can be generalized to more than two classes, right? So, for example, I have class A that are normal programs, class B that is ransomware, class C that is virus, class D that is malware, spying malware. So it can be two class or multi-class classification. As you get to have more classes, the problem is typically hard. And for this classification, there has been many algorithms that have been proposed over the years, right? It's also, indeed, they're continuously posing challenges and improving the algorithm. So how can we do this? Typically, we will focus on supervised learning, and in supervised learning, basically you are given a data set of elements with the correct labels. So I'm given, I don't know, 100 pieces of code that are normal code and another 100 that are malware. And I use that to build my classifier. So I have like a ground truth of a subset of the possible elements for which I know the result. So with those, I train a model, or I compute a model, which is typically called training. It depends on the model, as we will see. And then once I have built my model based on that data set, I can present it with new data, with new elements, and it will do the classification, right? Typically, in algorithms, machine learning, the computationally, the most demanding phase is the training, which you have potentially to deal with large data sets and do many iterations. But once you have your model trained, inference is typically faster. Training is typically done in a facility where you have like a data center or computer infrastructure that is fault tolerant, and there are no so hard constraints on power or computing electric power or computing power. Whereas inference may be done on the field, on an IoT device, on any type of device, on a medical device. So the requirements for the constraints for power and complexity are much harder for inference. So how is this training done? Basically, we split the data set in a training set and a test set and a validation set, and we train the model with the test set. With the training set. Then we test it with the test set, and then we do a validation. And this is done with different splits of the data to do what is called cross-validation, to ensure, basically where we're trying here to ensure that the model is not biased to the specific data set that we are using. The larger the data set, potentially the better the classifier and the less biased. Because if your classifier has a lot of degrees of freedom and your data set is small, basically, if you don't use this kind of splits, the model can actually learn the data set. but then it will not generalize well. This is called overfitting, and well, there are a lot of things in machine learning which probably most of you are familiar with. But anyway, we have this training data set. We train a model, and we have a model that we present it with an element, and it will tell us whether it is class A or class B. Which algorithms? There are hundreds of algorithms in classification. One of the simplest is the k-nearest neighbors. Then we have decision trees that are quite powerful when they are grouping. For example, in random forest, then we have support vector machines, neural networks, etc. So we're going to look at some of them, simple models, and see how we can exploit them for fault tolerance. Most algorithms have some intrinsic resilience to errors, and our idea is to exploit that to implement low-cost protection schemes. This has been widely explored for neural networks, because basically deep neural networks accelerators require a lot of hardware, and then therefore duplicating or triplicating to detect errors is not an option. But fault tolerance has not been that widely explored for simpler classifiers. So we will start with the simplest classifiers, which are very, very intuitive as well. So in k-nearest networks, is basically we don't have any training. We just store the data set. When we are presented with a sample, with a new element, we see which are the k-nearest samples according to symmetric in the data set, and we vote amongst those. And then we take the class of the majority. This is illustrated here in this, try to remove this. Okay. So here we have the gray point is the one we're trying to classify, and the yellow and blue ones are the ones from our data set, right? And when we are classifying, basically what we are going to do is take the nearest, in this case, k equals 5. So we take the 5 nearest neighbors, which are 4 are yellow and 1 is blue. And then based on that, we decide that most likely this gray element is yellow. Right. So a key observation here is that in a vote, for example, if here we have 5 yellow and we make a mistake in computing one of the neighbors, it doesn't really matter because it would not affect the decision. So we call that a voting margin. So when we have a vote among k nearest neighbors and there is a majority such that one error will not change the result, then we can live with that, and we don't need really to recompute everything. We just need to make sure that we have that margin, and then that's fine. By the way, I put on the slides the links to the papers where we describe this in more detail. So should anyone would like to look it up and see the details. If you have any questions, you can also send me an email or contact me, and I'll be glad to describe anything. So here's an example. So we have this 4 to 1, and suppose due to an error that yellow one is pushed out due to a computational error. Still we have 3 to 2. So still we're getting the correct result. So the fact that we had some margin allows us to tolerate errors without changing the classification result, which is in the end what we need. Here instead, what happens is that a blue one, due to an error, appears to be closer. Again, due to the voting margin that we have, we can get the correct result. So in this very simple classifier, whenever we have a voting margin, we can tolerate errors. So 4 to 1, if we started with 4 to 1, an error in the computation of one of these distances would just bring us to 3 to 2, which again would be the correct result. So there is no need to recompute when we have the margin. When we have no voting margin, here we have 3 to 2. So an error which pushes that away makes us pick the next one. If the next one has the same class as the one we push out, then the classification result is not changed as well. So we can also look at the class of the k+1 neighbor and use that to detect and correct errors. Instead here, if the class of the k+1 neighbor is the opposite, it would change the result. So basically for this very simple classifier, if we have a voting margin, we don't need to care. If we have just a very tight vote and there is no margin, we can look at the classes of the k and k+1 neighbor, and based on that also detect errors. So if we were to implement time redundancy in these systems without doing anything, without using the algorithm, we would run it twice and then make sure that we are getting the same output on both runs, and then we would say, okay, the result is error-free. Here with our scheme, what happens is if whenever any of those two conditions above our hold on the first run, we don't need to run the second time. So we are saving basically a lot of computations. So to evaluate this, we use a few data sets. Those are, for example, EEG is a medical data set, ionosphere is a physical data set, and we have also phishing websites, finance-related data sets. So there are many data sets available. If you play with machine learning, you probably know these data sets. And basically, we ran the KNN on all of them, selected the optimal parameter, but there's a fine-tuning also in the training phase in which you select the hyperparameters of the algorithm. Here, the only parameter is K. So you see here on the right for each data set, the accuracy in the classification that we got and the optimum K that was for which it was achieved. And then, so you see that, for example, for bound-node authentication, this algorithm achieves close to 100% accuracy. Instead, for ionosphere, it's only 60%. So we try to use different types of data sets with different accuracies, different values of K. And here you see what is the computation overhead. That is the number of inferences for which there is no voting margin and we need to recompute. And you see that in all cases it's below 50%. So we are at least reducing by 50% the recomputations to detect errors. And in many cases we are below 20%, 30%. So results are pretty good. This is again just for a very, very simple classifier. This idea of seeing if the first result on the first recomputation is already strong enough such that a single error would not have changed the sign of the output of the class selected can be applied to other types of machine learning algorithms. In machine learning, one of the approaches to build a strong algorithms is to combine simpler algorithms. That is known as ensemble classifiers. So we take many different machine learning models and we vote amongst them. And a typical example for this is forest, and in which we use individual classifiers are decision trees, and we use the trees to merge them together and achieve a good classifier. And random forests are an ensemble of trees are a much more powerful classifier than k-nearest networks in general. So this, in fact, is what we do ourselves as humans. For example, when we are trying to make our minds about something, try to make a decision, we probably ask 5 people, and if all 5 people say advise us to do the same thing, then probably we'll go with that. Instead, if 3 say something and 2 say another thing, then we will have more doubts about what to do. So this is basically the idea between ensemble classifiers. And a random forest is basically uses decision trees, which is a simple classifier, and it uses many trees. Here we are seeing a random forest that is using T trees, and the number of trees can be from tens to hundreds of trees. And basically each tree produces a class result, and then we vote among them. Again, as we can see, this type of ensemble classifiers lends themselves very well to the voting margin idea that we use initially for the K9 classifiers. So basically, when we have 100 trees and 99 are saying class A, we really don't care about any error on any single tree because it's not gonna change the result. So, in fact, in random forests, since we use many trees typically, the idea of the voting margin is even more powerful, right? Because we have many trees, so it's much more likely that we have margin, that we don't depend on a single tree to swap the classification decision, right? If we have 100 trees, probably we have 60 to 40 or 57 to 43 or something like that. It's very difficult that we have 51 to 49. So typically we have a lot of redundancy in the ensemble. So here are the results for a few data sets. In this case, since the classifier is stronger, we use multiple classes, right? These are data sets in which it's not A and B, but you have different classes, like 4 classes, 3 classes you have in the paper. Again, we try to use a balanced set of data sets so that they have different applications, different number of classes, different accuracies, etc., etc. And you see here, as the number of decision trees grows, the percentage of the computations that we need to do goes down typically, because basically we have more and more margin. And in both phases, you have the optimum, the value of the number of trees that was determined to be optimum for classification accuracy in the hyperparameter. So here you see that really this works extremely well. So basically for random forest, we don't need to do, it's very rare that we need to do recomputation. We just compute the forest and we go with the decision because a single tree will not change the result. So in general, this idea of having a voting margin is quite powerful, especially for ensemble classifiers based on trees. Let's look at another classifier, which are support vector machines. These are a different type of classifiers that use like an analytical equation to compute the class. And they use this can be done with linear functions, but this is typically not good enough. So they use what is called a kernel, compute a non-linear function that allows us to do a better classification. So conceptually, what a support vector machine is doing is taking the hyperspace of the features of which we are basing our classification and separating them into subspaces. In a linear classification, the problem is that the split has to be a plane, and that's not good enough when the data is not linearly separable. So you can use a kernel function, and with that kernel function, you can implement what we see on the right, with a more flexible boundary. So support vector machine basically computes this equation and takes the sign to determine the class of an element. And here, the kernel function is typically this exponential, which is the radial basis function. There are other functions, but this is probably the most well known. So basically, since we have this equation and the WI are the weights which are fixed, computed during the training, basically what we can do is again check the result before the sign and see whether a single term could have changed the recomputation, the classification result, right? If that's not possible, then we don't do to recompute. Again, these parameters are done, the WY are computed during this training phase, and then during inference, we just compute this equation, take the sign, and that's it. The most complex parts for this computation of the inference is basically the kernel function and the distance computations, which are basically over here. Again, since it's a negative exponential on a positive number, is bounded to be between 0 and 1, and this means that this term can never exceed WI. So it means that if a change of WI magnitude on this result doesn't change the sign, then we know we have margin and an error could not have affected us. So we can take the maximum weight of all across all these weights, and whenever the classification result is larger than that, then we know the result is solid. Any change on any weight would not change its sign. So this is illustrated here. Basically, we have these points. For this point, any change by the maximum weight doesn't preserve that. It preserves the sign. The change here. Instead, here it changed from here to here. We change from positive to negative, so we change the classification result. And here we are just on the limit. We will push it close to 0, so it's on the limit. So for the red points, we don't need to recompute. While here we need to do the recomputation. This can be pushed a little bit harder and look at it. Instead of looking at the maximum weight, look at each of the weights when computing each of the term. Instead of just looking at the result of the function, we can look at each of the weights, and for each weight, see if it would have an effect or not. This is conceptually the same, but now in this case, we are looking at each weight and see if each weight could move it or not. So the bottom line idea is basically the same. We compute the SVM result and we compare it to the weights. If the end result, the SVM result is large enough so that a single weight would not have affect us, then we don't need to recompute. So here I get some sample results for many databases, and we see this is combining this is for using all the weights, and this is using some range of the weights, and finally each weight independently. And this combines the results for this SVMs versus the KNS. And we see in many cases, we need to do similar number of computations for both, or in some others, the SVM are better. So again, instead for a few databases, these two, and note the percentage of recomputations is low. So again, we can save most of the recomputations without compromising the accuracy of the result, the classifying result. So let's look, although we don't want to focus on neural networks, which are quite complex, let's look a little bit at the simple example of neural networks. The simplest meaningful neural network is the multilayer perceptron with one layer, which is what we have here. So we have basically the features of the element we are trying to classify. We pass them through an input layer, a hidden layer of neurons, and then an output layer just to take the decision. This would be for a 2-class classifier. If we have more than one class, we would have more than one neuron. So basically, its neuron is doing some computation based on its inputs and computing an input value that is passed then through an activation function, and then goes to the output. So this is basically what a neuron does. Right? Neuron first computes the inputs multiplied by their weights with bias function, with a bias term, and then goes through an activation function. Now, for the activation function, there are many of them, like the ReLU, the sigmoid, the tank function. Here we're looking at the sigmoid. The sigmoid, which is one of the most commonly used one, which has again an exponential similar to the one we were seeing in these support vector machines, right? So when you look at the neural network, you have many of these neurons. Even for a simple network, you can have hundreds of these, and you have a lot of weights and a lot of connections. So typically what happens is that in many cases, most of the weights are small. So they will not change. Even if there is an error coming here, if this weight is small, it is very unlikely that it changes the result. So typically you have only a few critical nodes that are the ones that correlate with large weights. Things that you can try to do is to avoid large weights during training or by selecting the network topology, or to try to recompute only for those critical nodes. You can also try to build an example that is also done instead of using a very large complex neural network, use 3 smaller complex neural networks as an example, an ensemble. And then you will end up again with this voting margin idea that we just described, but applied to neural network. In this paper, what we did actually was to identify the nodes in the neural network that were critical and only do their recomputation selectively for those. So it's kind of time redundancy, but it's selective in the sense that we only do it partially for a few nodes, and that's enough. So as you can see, there are many types of classifiers, many implementations. Here again, we also focus on single failures on computational units. You can also look at permanent failures. You can look at multiple failures. You can look at FPGA implementations, and which you can have errors in the configuration memory, etc., etc. There are many failure models. There are many implementation platforms. There are many algorithms, and all of them you see are amenable to algorithmic-based fault tolerance, because basically all of the algorithms for machine learning have inherent redundancy that can be used to reduce the cost of protecting or detecting and correcting errors. In the presentation, I have gone quite fast over the machine learning and different algorithms and the methodologies used to train them. So here I have a couple of good books in case anyone is not familiar with machine learning and wants to play a little bit or wants to start looking into it. So you have 2 ones. Many of these books also come with code, and there are many sources online to play and test algorithms or test ideas if you have any idea. Okay, so it's, I think that's it on my side. I think that I ended more or less on time, a little bit ahead maybe. So I don't know if you have questions or things to discuss. I'd be more than happy to try to answer.
I guess I can start with questions. In terms of like any like new problems in this topic, anything you can like hint at least to our students, like what could be emerging research problems in the area? I
think there's a lot of interest in the fault tolerance of accelerators. There are many accelerators for neural networks. Mostly, many of them are mapped to FPGAs, and they use different architectures. Like some of them are based on like functional units, where instead of mapping the complete neural network to the FPGA, you map some of the neurons to the functional units and you recirculate the data and all that. The only problem there, to get into that, you have a large learning curve, right? You need to first get an accelerator, you need to run it, you need to understand it, then you need to inject errors on the FPGA, configuration memory, and all that. So I think that's an interesting topic, but it requires a lot of effort to go into that topic. And the injection time, you also need a lot of boards to do the injection time. I have done some works on that with some people from China, that they have all the infrastructure there. So I think that's one direction, but it's maybe for students it can be a little bit challenging, right, to do. And then for these simple algorithms, there are many algorithms, and probably, for example, looking at what happens when these algorithms are implemented on an FPGA and there's a failure on the configuration memory is interesting, because that failure model would be completely different to what we have considered in these works. So probably you can reuse some of the some ideas, but others you need to change. So I would say considering other failure models for these simple classifiers, or try to go deep into the accelerators, which I think would be quite challenging for us. I don't know if that is provides some information or not.
Thank you. Anyone else has any questions?
I can ask something, because so when you are basically analyzing the fault tolerance,
hello,
you're considering the let's say which kernels affect the result to have a, let's say, wrong classification or misclassification for that case. But in most situations, the weights are associated so that overall it represents something in the output. So one particular kernel or like associated weight is not that important. I mean, so basically analyzing the results through that, let's say, single kernel change, what do you think about, like, how accurate is it? Meaning that because my whole vector represents the output, so it's distributed among all the kernels in my structure. So one single kernel generally does not make that much of a difference if the training is done properly. Do you see what I'm saying?
So I don't know, maybe you are referring to the fact that even without protection, many of these classifiers will not fail. So
yeah,
they are...
I mean, mostly if the training is done properly, and if it's not overfit, and if the data is distributed, I mean, if there is not much problem with the data distribution, then most of the time singling out kernels might not make that much of a difference.
Yeah. So indeed, we didn't present results here, but even without protection, many of these classifiers will filter out maybe 90% or 95% of the errors, and they will not affect anything. So they are kind of resilient. The problem is when you're running this on a safety critical application, and that 95% of errors filtered by the design itself is not sufficient. We want to detect any error before changing a classification result. So for applications that are not safety critical, maybe in many cases you can rely on the resilience of the algorithm itself without doing anything. It's only when you want to really detect all errors when you need to use protection.
Okay.
Yeah, we did. I didn't discuss that. Maybe I should have. I started with that at the beginning.
Just to add something to the discussion, because let's say for the deep networks, most of the training includes some dropouts so that's exactly to prevent these sort of situations where, like, particular parts of the network should not be dominant in representing the whole, let's say, association. So that might maybe help in also those fault tolerant systems in that sense.
Exactly. In fact, yeah, I had not discussed that as well, but you can also introduce errors during the training and try the network to be error tolerant by the training itself. If you have Madrid'den, so you can train with data sets that have some errors if you want, and then maybe that makes the neural network more resilient. So for neural networks, there have been also papers trying to use the training and the design of the neural network itself to make it error resilient.
Okay.
Yeah, again, I wanted just to give some very simple ideas and general ideas, because I didn't know, maybe some of you are working on this topic, some of you are not. So I wanted to make it as general as possible.
Anyone else have any question? Any of the students? I guess not. Well, then, okay, there's a question in the chat. In real systems, how often do these errors occur?
This depends a lot on where the system is. If the system is in a terrestrial application, these are rare errors, right? They are very, very rare, but they do occur. However, if you are in a harsh environment, like in space or in avionics or in a particle accelerator, they are much more frequent. The problem is that they do occur, right? So, for example, in large data centers where they are running hundreds of thousands of machines, they get errors due to radiation every day, right? So it really depends on what you're doing. If you're just doing one system, but if you're designing something that is going to be run on every mobile phone, then it will get errors in some of them from time to time.
Any other question?
In any case, if anyone wants any further details or anything, I can provide pointers to other papers. Just send me an email and I'll try to help anyone interested in exploring this further.
Thank you so much for again accepting our invitation. It was a
Thank
very
you
nice
for
talk,
the invitation.
interesting topic.
Yeah, it's a different perspective on machine learning, right? You also have security, privacy, and reliability are now also hot topics in artificial intelligence. So it's something maybe that students can consider for their work.
Should we finish?
Yeah.
Would you like to say anything?
Pedro, thank you for coming. It's nice to see you again.
Hopefully we will see in person at some point.
Hopefully we'll meet again soon.
Thank you.
Take care.
Thanks a lot for your time. And again, if you need any information, just send me an email. Thanks.
Thanks for the presentation.
Thank you.